del square phi over delta plus plus del phi dot del of del phi dot phi over 2 is 0, and then the a square is equal to a infinity square plus gamma minus 1 over 2 u infinity square minus del phi dot del phi minus 2, okay, and then the pressure expression P equals P infinity into 1 plus gamma minus 1 over 2 A infinity square U infinity square minus del phi dot del phi minus 2 delta phi over delta t power gamma over gamma minus 1. And then you have the boundary condition, which is the boundary condition is delta f over delta t plus q dot del f is 0, where q is velocity, which is del phi. Okay. Now, this is our exact nonlinear potential equation. The kind of problems which we have to deal with in aeroelasticity, that makes simplification to this entire set of equations, and that is called the, because this is highly nonlinear, so you have to go for the small disturbance, okay, potential equation, which is the linearized equation which you will get. So please note that that is the small disturbance. Why small disturbance? Because we are going to treat with the wings, lifting surfaces. Lifting surfaces we can are thin aerofoil surfaces. This is along x, this is y, and you can assume this is the wing, so you can go, and this is the z. Now the f is the equation to the surface of the body, and which basically creates the disturbance in the flow. Now this approximation in representing f is actually responsible for reducing our equations to that small perturbation, because how we write, since it is the thin, relatively thin surface, we will write this f, which is a function of x comma y comma z comma t, as z is separate minus f of because equation of the surface. Okay. Now you can have a upper surface or the top surface, and this is the bottom surface. Okay. Now if you have a top surface, that F T is for top surface, which will be a function of x comma y comma t. This is top, and the bottom is, you can write F B, which is the x comma, okay, top and bottom surfaces. Now this is how we are saying that I am splitting, somehow the z is coming out, and I am writing the z, which is the location on the surface, is basically a function of x and y. Now if I have this type of representation, Ft and Fb, I will go back to the boundary condition. Now what is delta F by delta T? And this expression, if I write, this is delta F over delta T plus Q is del phi, which you can write it as U I plus V J plus W K, but I am going to use the U a little bigger U, because again I will split that into two parts, because one is the free stream velocity, which is along the x-axis. This I am going to write it as U infinity plus lowercase u I plus V J plus W K. That means my potential gives me the total velocity, gradient of potential, and my U infinity is the velocity far field. This lowercase u, v, w are essentially perturbations due to the wing or the airfoil, due to this submerged structure which is present in the flow. Now if I write this, because u infinity is the velocity of this whole thing, that is your speed of the aircraft or anything, the wing, and these are perturbations in the flow due to the presence of the wing. Okay. Now I substitute this back here, you will get u infinity plus lowercase u, del f is delta f by delta x, because this is a dot product. Then I will have v delta f over delta y plus w delta f over delta z. This is 0. Okay. Now I am going to substitute for f this expression. Okay. If I substitute this expression, because f is the equation of the surface at any time, if I substitute and then delta f by delta z, because this z, delta z by delta z, that is 1, independent of z, so that is 0, and you will have w, which is actually the flow velocity. It will become like this, w, which is the flow velocity, is going to become this, you will take it as delta f by delta z. Here all are lowercase f, because f is z, f minus x, z is independent variable, therefore that is not a function of time. Okay. And similarly here z will not come, here also z will not come, they will have a minus sign. So you transfer all the terms to the right hand side, you will get delta f by delta t plus u infinity plus lowercase u x plus v delta f by delta y. Okay. Now this is on, please understand, on z equals f of x comma y comma t. This is the surface. Okay, this condition is on this surface. W is the flow velocity, right? And you know that f is this function. Now you are going to make some assumptions here. That is, if the slope of the surface with respect to x, because we have drawn, this is z, y and x, our aerofoil, this slope with respect to x, delta f by delta x or delta f by delta y, they are small because it is not a large slope. So these slopes are small gradients. Okay. And then you say, this is again you are making an assumption that my u and v are also relatively small in comparison to u infinity. So you say my u, v and w, they are okay. This is an assumption I am making. Now if I neglect terms which are products of small quantities, that means this is a higher order term. Similarly, this is a higher order term. I will get here simply neglecting w approximately becomes plus u infinity delta f by delta x. Okay. That is, I am eliminating higher order terms. This is my, that approximation, later I will say this is equal to, that is all. Now I know the surface equation f of x y, this function, I will substitute u infinity, I know, I can know this. Only thing is my flow velocity must be equal to this. Flow velocity normal, whatever we said, w. W is along the z direction. Okay. Z direction where? Here again you make another approximation. That means W must be what? W must be on every surface point. But you are going to make an assumption that W, maybe I erase this part. Okay. You are going to expand it, that W, which is a function of x comma y comma z, okay, whether it is a top surface or a bottom surface, that will depend on whether z, if you put it top, because you want to calculate the flow velocity on the surface. So this can be, if I put it top ct, that means this is the top surface, and you are going to expand it like that Maclaurin series, because this you will write it w, which is x comma y comma 0 plus, this is an expansion about the z axis, plus you will write z top delta w by delta z at x comma y comma 0 plus comma t, plus higher order terms. Again, similarly for the bottom surface, you will put this is b, and you say that these are thickness is not very large, and the slope delta W by delta Z, that is the variation of the flow velocity with respect to Z, is not very large. That is, there is no sharp gradient in any of these things. This is an assumption. Then you say, I neglect this term. Okay? I neglect this term, and then I say that the W at x comma y comma z top surface T is 0 plus, and I am going to write similarly for the bottom W x comma y comma 0 minus comma t. Okay, which means I am simply satisfying the condition on this line. Please understand, on this plane. Only on the xy plane I am satisfying the condition. I am not really going and then satisfying the condition at the top surface. This is the aerofoil or the entire wing span. I will satisfy on this. That is why here I will write it on z equals 0. This I am satisfying the condition. On z equals 0, when I put plus, that is the top surface. When I put minus, that is the bottom surface. So as far as I am concerned, my W is only on this plane I am considering. Then you may ask, what happens to the thickness of this? Okay. That is why now you say you have to do one approximation, later we will go to that. The assumption we made is these surfaces are thin, and we can make, and the slopes, whatever the aerofoil shape which you make, the slopes are also very small. Therefore, we have neglected the higher order terms, that is the nonlinear terms. Because, and another assumption we made is that velocity u, v, w, which are the perturbational quantities, are small in comparison to the flow field, which is u infinity. So this is the basic assumption. Now we say all my quantities, that is the disturbance due to the presence of my airfoil, they are small. So this is called a small disturbance potential flow. Okay. For that, I am going to now modify the entire set of nonlinear equations into a corresponding linear equations. Okay. They will become a very simplified linear equation, and that is what we will use for our solution of the flow, supersonic flow, subsonic flow, everything. Okay. So this is, please understand, the assumptions we make, everything is purely based on the boundary condition, because you say my surface is thin, it's not going to disturb the flow. You are not going to put a building over there and then try to solve this problem. In the sense, you have so much of disturbance. We are saying our surfaces are thin surfaces. Okay, lifting, because that is where aeroelastic problems are important. That's why this assumption is made. Thin aerofoils, that's good enough. And finally, the proof is, if you can get a solution which is good, which is matches with an experiment, that is where the theory gets validated. Okay. Now let us get the formulation for a small disturbance potential flow. That means the reduction of these equations as well as all the, so the boundary conditions, please understand, this has been modified to this. Okay. This is my boundary condition now. W is the flow velocity, please understand. Flow velocity and we are looking, W is flow velocity everywhere, but we are matching the flow velocity to the surface on z equal to 0 plus minus only along the up to the card and the wingspan, that is all. If it is a 3D problem, it is a wingspan. If it is a 2D problem, it is only card. Okay. Now there will be other, what happens to the off body boundary condition? There is something like that we will do when you, what happens to the thickness? Does it do anything? That we will do off body condition later. Because right now we will say this is my boundary condition. We will reduce the set of equations, and then if possible we can do right away itself that off body also, because that will also give me, we can do both. 1 minute, we can do the, okay, let me finish the linearization first, okay, and then I will take the, because that is a very interesting condition. Please understand, this is the key. We have converted this to this. Okay. Now what is W? W is delta phi by delta z. That's all. Delta phi by delta z at z equal to 0 plus or z equal to 0 minus. Okay. But please understand, on the aerofoil, Z top surface, bottom surface, they are different. Don't mix these two. That is why it is very essential that when you put the top surface, bottom surface, the F is correspondingly going to change. F for top surface, it will be top surface, and FB, it will be bottom surface. That's all. Okay. Now let us take the reduction of the equation. Okay, because I will keep this. This I leave it as it is, because this is important, your boundary condition. Okay, we are going to now use the condition that A, the speed of sound, A infinity plus A hat. Some small, these are small disturbance. That is the small perturbation quantities. And the pressure is P infinity plus P small, and density rho infinity plus rho hat, and your Q, that is the velocity. Velocity is U infinity I plus, where Q is Ui plus Vj plus Wk, and your phi is U infinity x plus phi hat, and you know that Q prime, this is nothing but del phi hat. Please note that del phi hat is this, okay, like what we wrote earlier. So from the boundary condition only I am bringing it here. Now why I am saying from the boundary condition, you may ask the question. See, I am saying the disturbances, because this boundary condition is only near the surface of the wing. If I can make an assumption that my UVW, that is the perturbational velocities, they are small near the surface, the boundary, then I can make an assumption that far away from that they can be small. Okay. Please understand, this is an assumption, because I say that the disturbance to the flow is created by the presence of the aerofoil. Near the aerofoil, the disturbances are small. Therefore, I say that okay, far away from that, the disturbances will be still smaller. Therefore, I am making all these assumptions that everywhere UVW is small in comparison with U infinity. But see, this is a very interesting question, which comes. The disturbance is small near the boundary, which is the disturbance causing surface. But how can you say that far away it will be less? Okay. This is an assumption you make because is there a counter example where it is not? Because this is very interesting. Suppose you take the tsunami. The disturbance wherever it has caused is small, but then it built up far away from there, and then you had floods only somewhere several miles away from the point where the earthquake or anything has happened. You follow? Now the question is there, how can you say the disturbance is small there, but then it built a catastrophe in some several 100 miles away from that? It's a very difficult thing to answer. See, that is a surface wave, but here we are making that assumption that whatever near the aerofoil disturbance is small, it is not going to grow far away. Okay. Now with this assumption, what we are going to do is we are going to substitute these quantities, because phi, you know this, I am going to put this back there, del square phi. Okay. Now when I put del square phi term by term, if we go, then you will find that everything will be, what if I do? Okay. Okay. The first term del square, because I am going to substitute this. Okay. When I substitute this, that will become del square phi is going to become del square phi hat. There is no problem. That is the first term, because this is a little bit of algebra. And the second term, which is del square, I will write it here, okay, del square phi over delta t square plus delta by delta t of del phi, this is the second term. Plus del phi dot del of del phi dot del phi over 2. Okay. This is, because when I substitute this, it is independent of time, because u infinity x is not there. So this will become del square phi hat over delta t square. This is nothing but q dot q. Okay. So q dot q is q square. So you will get, when you differentiate, that will be 2q. So you can write it as plus 2 q dot delta by delta t of q. Q is given here. So I can write it as 2 u infinity I plus this q prime is what? Q prime is del phi. So I am going to put plus del phi hat dot delta by delta t of u infinity I plus again del phi hat. Okay. That is this term. Same. Then you have to write the last term. Last term is plus del phi is nothing but u infinity I plus del phi hat dot del of This is del phi dot del phi. Okay, that is nothing but this dot this. This dot this nothing but u infinity square over 2 plus u infinity I dot del phi hat plus half del phi hat dot del phi hat. Okay, and this is what you do is you neglect all the non-linear terms. This will essentially reduce to, maybe I erase this part. Okay, I will write it again later. This will again become, this term will remain as it is. You will have what you do is you substitute everywhere delta by delta t. This is gone because this will go to 0. There is no, it will not be present. But this del phi is nothing but delta phi by delta x I, delta phi by delta x j, etc., etc. Okay. Then this is also del phi. This del phi, they will become higher order terms. So you take only u infinity I and the I of this term. Okay. That will be a linear term. So you neglect all the non-linear terms from here. Okay. Retain only the linear terms. So if you want, I will write the whole thing, then we will del square phi hat over delta t square plus 2 u infinity I plus del phi hat dot of, you will have del square phi hat by delta t delta x I plus del square phi hat delta t delta y j plus del square phi hat by delta t delta z k. Okay, plus you will have this entire term. Okay, that the entire term again you can write it as plus u infinity I plus del phi hat dot see, this is u infinity, this is del of u infinity square because u infinity is a constant. Okay, so this will just drop off, it will not exist because this is a gradient of a constant, so that will go off. Okay, so you will have dot u infinity del square phi hat by delta x square, okay, I plus del square phi hat by delta y delta x j plus del square phi hat by delta z delta x k plus half this whole thing, because I am taking dot product of what, this into this, because this term as it is remaining here. Please understand, I am taking this del, this I will have only I term because this is the u infinity I. So I will get only delta phi by delta x phi hat. That is why I have delta phi hat by delta x, this delta by delta x I, this is delta phi hat delta x, then delta by delta y j, delta x delta by delta z k, and u infinity is this u infinity there. Okay, because this term only I term will survive, rest of the terms will be 0 because I dot j is 0, I dot k is 0. So this will simply means u infinity delta phi by delta x, delta v, and that you take a gradient. Okay, and this is half the entire term that you can take it as half. You will have here I, j, k. So you will write it as delta by delta x of u square plus v square plus w square I plus delta by delta y of u square plus v square plus w square j plus delta by delta z of u square plus v square plus w square k. So you see, this is a very complicated expression. You simply throw away all the non-linear terms. Okay, that is what is done. Please understand. Otherwise, if you expand, this is going to be very big. So you neglect the nonlinear expression and write it as, I'll write the final result here. Okay, the final expression will be approximately del square v hat delta t square plus 2 u infinity, that is this term, del square v hat by delta t delta x plus, you see this term, u infinity I and u infinity square delta phi by delta x plus u infinity square del square v hat by. That's all. The rest of the terms I am neglecting it. Okay. So you see, when I neglect the rest of the terms, this becomes very simple. This is a linear operator. Okay. So I erase this part and I will write my equation here. Now you also have to see what am I going to do with this term, because here it is a square. Okay. A square is again a function of phi. Okay. This is not an independent. Now I say the perturbation and other things, I am going to assume a square is a infinity square, because the moment I make that it is not, then it is again a nonlinear equation, because I am going to get phi here and this will be denominator. Okay. So it will become again a nonlinear. That is why I will write this term as this and a square as simply a infinity. So my small perturbation, it will be del square phi 1 over a infinity square del square phi hat by delta t square plus 2 u infinity delta phi del square phi by delta t delta x plus u infinity square del square phi hat by delta x square. Okay. Please understand, this is my unsteady small disturbance linearized potential flow equation, because this is a linearized, and this equation, please understand, this is a linear, completely, absolutely no problem. You have a linear equation. Okay. Now what are we going to do with the pressure expression? And for the so let us erase this part and we will write the pressure expression as well as the disturbance, because even though I use here a infinity square, but I can get an expression for local speed of sound. I can get an expression for a local speed of sound. I am going to write that as a as some a infinity plus a So I substitute that here. What will happen? A infinity square will cancel out. So you will have a hat square plus 2 a infinity a hat equals gamma minus 1 over 2. You will have u infinity square minus, this is del phi dot del phi, which is nothing but again u infinity plus u whole square plus v square plus w square minus okay minus 2 delta phi over delta t. Now what I can do is I can again make an approximation that okay, this a hat is small, therefore I throw this term out and I am just using only this term, which is like my a hat will become gamma minus 1 over 4 a infinity. This is what? U infinity square will go away, leaving behind you will have minus 2 u infinity u. So I am going to use only that term, minus 2 u infinity u, and rest of the v square, w square I am saying they are small, I neglect that, minus 2 delta phi over delta t. Okay. So this is what I call it as change in the local speed of sound. Now if you see, u is delta phi by delta x, this term, that is del phi hat by delta x, okay, that is what, and this is anyway phi becomes this phi hat, because there is no u infinity is independent of time. Now you see u infinity by a infinity, this is the Mach number. So long as the Mach number is not very large, this speed of sound variation is not greatly affected. Okay, that's why Mach number, but very large, what is very large is another question. That is why we will use, please understand, we are going to use the same equation for supersonic flow. We are not going to use some other, because we say so long as the Mach number is not very large, below Mach number 3, because there are other problems, heating, local heating, everything will come. We have isentropic flow, we made isentropic flow as an assumption. Okay, so based on that assumption we say up to less than Mach 3, less than 3, these equations are fairly good. Okay, and that's why these are used, potential flow, small disturbance. Now let us go to the pressure expression, because this is the change in the local speed of sound. Okay, this is just for exercise. Now let us look at the, I erase this part, let me write the pressure expression. Okay. The pressure is this. I am again making assumption that all these are small quantities, so gamma minus 1 I am going to expand by binomial. When I expand by binomial, this will go here inside, and I retain only one term. I will not retain more than any term, because this is 1 plus something power x, something power. I say that this quantity is a small quantity. Therefore, I will get my pressure is P infinity times 1 plus, because if I take this, this will become gamma over, you can take it actually after simplifying, you will get a infinity square, because u infinity will go off square, and the factor 2 will cancel with the factor 2 and another factor 2 here, like what we did earlier. Okay, you will get basically minus u infinity into lowercase u, which is delta p hat over delta x minus delta P hat over delta T. Okay. And this I can write it as P minus P infinity. Okay. What is this? This is A infinity square is gamma, right? So you will get P infinity gamma over A infinity square is nothing but rho infinity. So I will write this is rho infinity times U infinity delta P hat over delta x plus delta P hat over delta T. This is basically the change in pressure. Change in pressure at any location in the flow. Okay. This is my, I can get the pressure coefficient if you want. Cp is nothing but P minus P infinity over half rho infinity U infinity square. You divide by that. So you will get minus 2 over U infinity delta P hat over delta x minus 2 over U infinity square delta P hat over delta x. Sorry, delta T. Okay. Now you see, this is my equation and my boundary conditions are W is what? Delta F by delta T plus U infinity delta F over delta x. But this W is delta P hat over delta Z at Z equal to 0. You can have plus or minus because F top, F bottom, that's all. Now this completes your entire problem. Okay. Now is that all? Is a question. Okay. You follow? Now you have, see, I will not be using hat from now on because it is not necessary. I have to, because when I use phi, you assume that it is the perturbation only, because just for again everywhere I have to put hat, that is just for convenience. I am eliminating the hat from the all these equations. I will use only this equation, okay, and this equation. That's all. My local speed of sound, small disturbance, you can get always what is the local speed of sound. That's all if you want to get it. So now this is your, you can say you are linearized about this is a small perturbation, I would say, because these are all U infinity you say is large in comparison to your perturbation. Okay. And when we solve our equations, whether it is a supersonic 2D or subsonic, we are going to use only this. But then if you see incompressible, you go, that means you are going to say A infinity is very large. Okay. So this term goes to 0. I am left with just a Laplace equation, del square phi equal to 0, whether it is a steady flow or an unsteady flow. Please understand, I have my solutions, the equation is same. Now the steady or unsteady depends on only the boundary condition. Okay. If my boundary condition F is independent of T, That's all. My boundary condition W is U infinity delta F by delta X. That's all. And my pressure, this will go off. This term will go off, rho infinity U infinity delta P by delta X. So I need to get only this is the change in pressure. Now you get pressure on the top surface, pressure on the bottom surface. And then you subtract that and you will get your lift. And you integrate over the chord of the airfoil. So you find finally all our entire unsteady aerodynamic equation is reduced to solving this. Only thing is thickness still we have not brought in, because we say this W, the flow velocity on the surface, but that F we have differentiated between a top surface and a bottom surface. Okay. Now what we will do is we will split that into two parts. The boundary condition itself, taking into account the thickness of the airfoil, and then by argument we will say that the thickness is not necessary to solve. So symmetry and anti-symmetry. See, we say this is our X, this is our Y, and this is a Z. And our, if we say this is my airfoil, let me cut it out. Okay, let me not bother about the Y. This is the top surface. This is the bottom surface. Okay. But I can write this as some midpoint I take. So I am going to write the upper surface F top surface, which is our F, is Z top surface, which is a function of x comma y comma t, because this is the function of x. I am going to write it of two parts. One is z t, you take it as t is thickness, this is zt. Okay. You may say zt by 2, but the 2 is absorbed in z itself, plus z lifting. This is the that is as though I can split into two parts. One is the thickness, another one is the lifting component. That means I am writing the surface, this surface, as though this is this surface plus a small thickness. And similarly F bottom, this is Z bottom, which I will write, this is minus okay, because the thickness is negative. Okay. So this is the mid plane plus some thickness, mid plane minus thickness. Thickness is actually Zt by 2, but it does not matter. Now if I am going to use this condition, that I can split my top surface and bottom surface into two parts, as though I can add these two. Then I am going to substitute, one is the lifting case, another one is the thickness case, because this I am writing it in a linear combination and all my equations are linear. Please understand, this is a linear, this is linear, this is also linear. There is no non-linearity in the problem. Therefore, I am saying I am splitting my problem into thickness case separately, lifting case separately. Okay. Now, if I look at the boundary condition is what? Delta phi by delta z, if I write thickness case, okay, thickness case, what is the boundary condition? Boundary condition will be upper surface and then lower surface. We will have two conditions, okay. In the upper surface, I will have what? I have to substitute here in the F, upper surface, top surface. Top surface is ZT. So I will put delta ZT over delta T plus U infinity delta ZT over delta X, okay, equals delta phi over delta Z, Z equal to 0 plus, okay. And on the lower surface, which is the bottom surface, I am going to put what is the bottom surface for thickness. This is minus ZT. So I will have minus delta ZT minus U infinity delta ZT over delta X equals delta phi over delta Z at Z equals 0 minus, okay. Now you look at this. This is delta phi by delta Z is antisymmetric because 0 plus, 0 minus. 0 plus is positive, 0 minus is negative. That means delta phi by delta Z is, for thickness case, is antisymmetric, okay. If this is antisymmetric, phi is symmetric. Phi is symmetric with respect to what? Only with respect to Z. Symmetric. Okay, antisymmetry, symmetry with respect to Z. Okay. If phi is symmetric, that means the top surface phi, bottom surface phi should have the same value. Now if I go to the pressure, P minus P infinity. This is, if I take it P top surface, it will be P top surface minus this. P bottom surface, it will be P bottom minus this. But my phi is symmetric. Symmetric with respect to Z. But delta phi by delta X is same. Okay. That means at 0 plus and 0 minus, it will have the same value. Therefore, it will not give me any lift. Okay, I cannot get any lift because of the thickness. Okay, so the thickness effect has no meaning. Only for all these linear problems, I am telling you, because it will not give. Phi is symmetric, therefore the pressure is also, P is symmetric means what? Pressure is also symmetric because pressure is delta phi by delta X only. With respect to Z, it is symmetric. Z plus, Z minus, it will have the same value. Okay, symmetric value. Okay. Therefore, this will not contribute anything to the pressure. Now, if you go to the lifting case, okay, you will get delta phi by delta Z, it will be symmetric. Therefore, if delta phi by delta Z is symmetric, that means phi is antisymmetric. If phi is antisymmetric, then this is antisymmetric. Top surface, bottom surface will have different value. Okay, then you can get the pressure difference, and that is what you will get it as the upward force. Okay, so we will write that part in the lifting case. So now you got it. Now this is, please understand, this is the place where your wing is there, your surface, because we are applying this boundary condition only on that, not in the free flow. This is on the body, okay, thickness case, and then let me write the other case. Okay, I erase this part. Okay, after that we will go to, this is in the lifting case. You will have upper surface as usual. You will have delta Z L over delta T plus U infinity Z L over delta X, which is 0 plus, and lower with a minus sign, sorry, this is a plus sign, plus U infinity zero minus. Therefore, I knock this out. You will have delta phi over delta Z symmetric with respect to Z. So phi is anti-symmetric with respect to Z. Okay. If phi is anti-symmetric with respect to Z, I can write my pressure. Okay. Because this is the upper surface, lower surface I can take. Okay. So upper surface means Pu minus P infinity, I will get one value. Lower surface, again PL minus P infinity is this. So if I subtract upper minus lower, which is the delta P, change in pressure, differential pressure, P upper, this is essentially, I write this term, because P infinity is anyway common term that will go off. You will have minus rho infinity delta phi over delta T plus delta, sorry, X. This is Z equal to 0 plus minus of minus. So I will get plus. Okay. Rho infinity U infinity delta phi over delta X plus at Z equals 0 minus. Okay. If phi is anti-symmetric means, then what will happen? This term will become minus. On the top surface, phi s, this will become minus. So your net term will become minus 2 rho infinity U infinity delta phi hat over delta X delta T, Z equal to 0 plus. So you have a pressure difference. That is because of your lifting. Thickness will not contribute. Okay. Now the question is, what are the off body boundary conditions? This is on the body. Now off body boundary conditions, you have to again write it for the lifting case and thickness case, because this is essential if you want to solve the full problem. So I will write that part. Maybe I erase this here. Okay, not necessary. I will write here off body boundary conditions. off body conditions you can say. Okay. See, off the body means your velocity must be continuous and the pressure must be continuous. That means let us look at the, it is only the z equal to 0 plane is important. So, z equal to 0 plane, okay. You will have pressure upper is equal to pressure lower, it must be there, and velocity must be continuous. So, you must get delta phi over delta z, upper surface must be equal to okay, because particularly this is very important for the q dot n, because velocity is continuous, normal velocity has to. Now, if you take this condition, if you look at it from here, thickness case, what does it say? Delta phi by delta c is antisymmetric. That means, but I want delta phi by delta z to be same, which means thickness case, okay, thickness case wants W0, because there it says antisymmetric delta phi by delta c. Here it says that means I want W0. That means there should be no vertical velocity in the backside. Now, if you go to the lifting case, this phi is antisymmetric. Okay. That means phi is antisymmetric means what? Your pressure upper and lower are opposite. Whereas here it says Pu must be equal to Pl, which means the pressure should be 0. Pressure should be 0 means that pressure should be P infinity, that is all. Okay. So, there is no pressure change. So, for lifting case, pressure P minus P infinity must be 0. This is off body boundary condition. Okay. This is on z equal to 0, this is off body. Thickness case says that W must be 0, okay, and then lifting case says that P minus P should be actually P infinity. Now, this is what is used in getting solutions later, off body boundary conditions, okay.